Beneath our feet lies a world that most people never think about: a vast network of tunnels, pipes, and chambers silently carrying away the waste of billions. It's invisible, but essential. Without it, civilization itself would collapse. Water, the essence of life, becomes our greatest threat when it's dirty, unmanaged, or ignored. This is the story of how humanity learned to tame it. Long before skyscrapers and smartphones, ancient people realized one uncomfortable truth: what we flush away defines the health of a society. 5,000 years ago, in the Indus Valley Civilization, engineers built one of the earliest urban sanitation systems ever known. Archaeologists in Mohenjo-Daro discovered homes with private bathing areas, drainage channels, and even street-level sewers. Each house was connected to a main drain, a stunning achievement for 2600 BCE. These early systems weren't just about hygiene. They reflected how early humans saw themselves as part of an organized society where cleanliness meant civilization. Meanwhile, in Mesopotamia, clay pipes carried stormwater and waste away from temples. The Babylonians already had rules for keeping water sources clean, and in ancient Egypt, the Nile served as both lifeblood and danger. Cities along the river learned to divert waste downstream, away from drinking zones, an early form of environmental management. But it was the Romans who transformed sanitation into an art of engineering. In the 6th century BCE, under the rule of King Tarquinius Priscus, they built the Cloaca Maxima, Latin for the Great Sewer. It started as an open canal to drain marshlands, but evolved into a vast underground tunnel system that still functions in parts of modern Rome today. The Romans didn't just want to manage waste, they wanted control. Their public baths, aqueducts, and fountains made water a public spectacle. For them, clean water was power, and the ability to remove waste safely was the foundation of empire. But despite all their brilliance, Roman engineers didn't fully understand bacteria or contamination. Their systems mixed human waste and stormwater. Many citizens still dumped garbage into the streets. So while aqueducts brought life, disease still lingered in the shadows. When Rome fell, so too did the infrastructure that made sanitation possible. For nearly 1,000 years, Europe forgot the lessons of the ancients. Cities grew, but sewers decayed. In London and Paris, people threw waste out of windows onto crowded streets. Streams became open sewers. Rivers turned brown and fetid. It was during this era that diseases like cholera, dysentery, and the Black Death spread with terrifying speed. No one yet knew about microbes. People believed bad smells or miasma caused sickness. Even so, a few thinkers began to suspect the truth. By the 16th century, early public health pioneers argued that clean water was not just a luxury, it was survival. The 17th and 18th centuries brought reason with it. The scientific method. Microscopes revealed a new world, microorganisms. In 1676, Antony van Leeuwenhoek peered into his lenses and saw animalcules, tiny creatures swimming in a drop of water. For the first time, humanity could see the invisible enemies in contaminated water. Still, cities kept growing and so did their waste. The Industrial Revolution turned the problem into a crisis. Factories lined rivers, dumping dyes, chemicals, and sewage directly into the same water people drank. In London, the River Thames became a toxic soup. By 1858, the stench was so unbearable that it became known as the Great Stink. Politicians fled the Parliament building, their meetings suspended because the river's odour made breathing impossible. It was only then that the world began to take sanitation seriously. In response, Sir Joseph Bazalgette, a visionary civil engineer, designed a network of over 1,300 miles of underground brick sewers that would forever change urban life. He overbuilt everything, doubling the pipe diameters and capacity for the future, a decision that still serves London today. His work marked the dawn of modern wastewater management system, where human ingenuity met civic responsibility. From London's model, cities like Paris, Hamburg, and New York began building similar systems. In the US, engineers adopted separate storm and sanitary sewers, a key innovation to prevent overflow and pollution. By the early 20th century, the idea of sanitation as science had taken root. Universities began teaching civil sanitation, what we now call environmental engineering. Wastewater wasn't just something to remove anymore. It was something to understand, treat, and recycle. New technologies appeared. The activated sludge process in 1914 revolutionized treatment. Chlorination became a public health hero, and biological treatment tanks mimicked nature's cleansing power. By mid-century, cities could clean water to near-natural levels and reuse it safely. The hidden world beneath our streets had become a triumph of design, science, and perseverance. As the 20th century progressed, awareness spread worldwide. Tokyo, Singapore, and Seoul invested billions in advanced treatment plants. In developing nations, NGOs and governments raced to install safe sanitation in rural communities. The World Health Organization declared sanitation a basic human right. Yet, billions still lacked access. Even today, over 2 billion people live without proper wastewater treatment. And over 80% of the world's sewage flows untreated into rivers and oceans. This, then, is where our story truly begins. Because the challenge is no longer just to dispose of waste, it's to transform it, to see it not as garbage, but as a resource. The next chapters will take us deeper, inside modern treatment plants, through the invisible microbial ecosystems, and into the future of AI-driven water management. From ancient clay drains to smart digital sewers. Humanity's struggle with wastewater mirrors our evolution as a species from survival to sustainability. And the deeper we look into what flows beneath us, the more we understand what it truly means to build a civilization. But if the Roman sewers were the birthplace of sanitation, then modern wastewater treatment plants are its high-tech descendants, quiet cathedrals of steel and concrete that keep our cities alive. Every flush, every shower, every sink, billions of liters of water flow here every single day. And what happens next, most people never see. Today, we're going inside one of the most complex and essential machines humanity has ever built, a modern wastewater treatment plant. Our story begins where the city's veins converge, massive underground pipes channel raw wastewater into the plant's inlet chamber. Here, the flow is chaotic, unpredictable, and filled with surprises: plastic bottles, wipes, sand, even toys or jewelry lost down the drain. So the first line of defense is the screening system. Giant metal bars called bar screens catch large debris as the water rushes in. Some are cleaned by hand, others by automated rakes that lift, shake, and scrape off waste into containers. What we remove here might seem trivial, but imagine one bottle cap jamming a pump and an entire city's system could grind to a halt. Behind the screens, grit chambers slow the water just enough for sand, gravel, and heavy particles to settle out. The lighter organic materials continue forward, the beginning of their transformation. Now, the real treatment begins, not with chemicals or magic, but with the simplest force in nature: gravity. The water flows into massive circular tanks called primary clarifiers. Each one can hold millions of liters. As the flow slows, suspended solids, mostly organic matter, gently settle to the bottom, forming a dense sludge. At the surface, oils and grease rise, forming a floating scum that is skimmed off mechanically. What remains in between, the clearer liquid, called primary effluent, still carries billions of microscopic organisms and dissolved nutrients. But it's already much cleaner than when it arrived. Typically, 30 to 40% of solids are removed at this stage. Now comes the most fascinating part, where biology takes over. Nature has always known how to clean water. We simply gave her a place to do it faster. This is the aeration tanker, vast basin where microorganisms feast on the organic material suspended in the water. Air bubbles continuously rise from diffusers at the bottom, delivering oxygen to keep these helpful bacteria alive. These microbes, mostly aerobic bacteria and protozoa, multiply rapidly, forming tiny clumps called flocks that trap and digest pollutants. The aeration process can last from 4 to 8 hours. During this time, billions of invisible workers are breaking down waste, transforming it into harmless biomass, carbon dioxide, and water. It's like a living factory, self-sustaining, endlessly adaptable, and millions of years older than any human invention. The mixture of water and biological flock is called mixed liquor. From here, it moves into the next stage. After the frenzy of the aeration tanks, the flow enters the secondary clarifiers, large circular basins where movement slows to almost stillness. Here, gravity once again performs its quiet miracle. The biological flocks, now heavier, sink to the bottom, forming a thick, activated sludge blanket. Clear water, called secondary effluent, rises to the surface and spills over the edges into collection troughs. A portion of this sludge is pumped back to the aeration tanks. This is called return-activated sludge to keep the microbial population thriving. The excess, called waste-activated sludge, is sent to be further processed off and turned into biogas or fertilizer. At this stage, the water is 85 to 95% clean, but not yet safe to release. There are still nutrients, pathogens, and trace chemicals to deal with. Modern plants often include a third stage, known as tertiary or advanced treatment. Here, the goal is perfection, removing what the eye cannot see. Techniques include filtration through sand or membranes to remove microscopic particles, disinfection using chlorine, ozone, or ultraviolet light to neutralize remaining bacteria and viruses, and advanced processes to strip away nutrients like nitrogen and phosphorus, which prevents algal blooms when the water is discharged. The result is crystal clear water, often cleaner than natural river water. In some cities, this reclaimed water is reused for irrigation or industrial cooling. In Singapore, they call it Uni water, a symbol of independence. In California, it's pure water San Diego. In the desert, it's survival. But what happens to the sludge? For every liter of wastewater treated, a thick layer of sludge remains rich in organic matter, but also in potential. In older systems, this was a problem. Today, it's an opportunity. The sludge is pumped into anaerobic digesters, huge, sealed tanks where bacteria work without oxygen. They break down organic matter into biogas, mostly methane and carbon dioxide. This biogas can be captured and used to generate electricity and heat, powering much of the treatment plant itself. The remaining solid material, after drying, becomes biocellulose, nutrient-rich substance used in agriculture. It's poetic. Really, the waste that once threatened human health now fuels the very systems that protect it. Modern plants are not only biological marvels, but also digital ones. Every pump, valve, and sensor is monitored in real time through SCADA systems. Operators can adjust oxygen levels, chemical dosing, and flow rates from a central control room. AI systems now analyze data to predict maintenance needs or optimize aeration, reducing energy use by up to 30%. A century ago, an engineer used to walk miles of pipes with a lantern. Today, the same system can be managed from a tablet. After all these stages, the treated water now clear, clean, and safe as released. Depending on regulations, it may flow into a nearby river, lake, or ocean. In some cases, it's pumped to reservoirs for reuse, watering crops, cooling factories, or even recharging groundwater aquifers. Every drop released is a promise that technology and nature working together can sustain life without destroying it. If you stand at the center of a treatment plant, you might hear a strange kind of music, the steady hum of blowers, the soft gurgle of aeration tanks, the rhythmic spin of clarifier arms. It's a symphony of science, tuned not for applause, but for balance, balancing the needs of humanity and the planet. Every flush begins a journey, and every journey ends in transformation. What we call waste, nature calls renewal. What was once unseen and ignored is now revealed, the invisible heartbeat of every modern city. Next, we'll travel even deeper, beyond machines and pipes, into the microscopic universe that truly cleans our water. Imagine looking into a single drop of wastewater under a microscope. To the naked eye, it appears calm, perhaps a little murky, but otherwise unremarkable. But zoom in, magnify it 1,000 times, and you'll find a city within a city. A teeming, bustling metropolis of millions of bacteria, protozoa, and microscopic worms. They are living, breathing, and most importantly, wet. These tiny organisms are nature's own engineers, the unsung heroes performing one of the most vital tasks of all, cleaning our water. Without them, the entire infrastructure of modern wastewater treatment would collapse in a matter of days. In every biological treatment plant, the heart of the system isn't the complex machinery or the massive concrete tanks, the activated sludge. This brownish, bubbling, frothy mix is profoundly alive. It's a carefully cultivated ecosystem containing billions of microorganisms per liter that voraciously consume organic matter. They are turning the pollution from our homes and industries into harmless byproducts like carbon dioxide, nitrogen gas, and clean water. Think of it as a natural, self-sustaining recycling center, operating 24 hours a day, 7 days a week, without ever demanding a paycheck. It is biological alchemy on a grand scale. Within this living soup, there are two main bacterial workforces in action: the heterotrophic bacteria and the autotrophic bacteria. The heterotrophs are the cleanup crew. They are the decomposers, feasting on the organic waste of food scraps, human waste, and other carbon-based pollutants. They break down these complex materials into simpler, more manageable compounds. Then the autotrophs take over. These are the specialists, particularly the nitrifying bacteria. They handle the intricate, invisible chemistry of nitrogen. They convert toxic ammonia, common byproduct of waste, first into nitrite and then into nitrate. Finally, another group of bacteria converts this nitrate into harmless nitrogen gas, which safely escapes back into the atmosphere. This elegant nitrogen cycle, happening in tanks all over the world, is one of the most beautiful and essential examples of biological balance in action. But bacteria rarely work alone. In this microscopic metropolis, they form intricate communities known as biofilms. A biofilm is a slimy, sticky, cooperative matrix where different species of microbes attach to surfaces and collaborate. You can picture it as a living city built upon particles of sludge or the walls of the reactor tanks. Within this city, each species plays a specific role. Some consume oxygen, creating oxygen-free zones for others to thrive. Some specialize in breaking down complex fats and proteins, while others even hunt other microbes. It's a dynamic, self-organized ecosystem in perfect harmony, a system that has been refined by evolution over billions of years. And let's not forget the predators of this microscopic world, the protozoa and rotifers. These slightly larger organisms act as the quality control officers of the entire system. They graze on free-floating bacteria, keeping their populations in check and ensuring the water leaving the system is clear and clean. They are the lions and wolves of the microbial Serengeti. When treatment plant operators look under their microscopes and see healthy, active protozoa swimming around, it's a clear sign that the entire ecosystem is thriving and in balance. Their presence is a biological indicator of a job well done. What's truly fascinating is how incredibly adaptive these biological communities are. If you change the temperature, alter the type of waste entering the plant, or adjust the oxygen levels, the microbial community responds almost immediately. Within hours, the dominant species shift and new balances are established. The system self-regulates. It's like having an invisible workforce that automatically retrains itself for new and challenging conditions. This natural adaptability is now being enhanced by human technology. Some of the most advanced treatment plants are using AI-powered monitoring systems to analyze microbial patterns in real time, identifying the types and numbers of organisms present. This allows them to predict potential imbalances or problems long before they can affect the treatment process, making the system more resilient than ever. So, the next time you flush a toilet, wash your hands, or drain your sink, take a moment to remember this hidden world. As the water disappears down the drain, it's not heading into a sterile chemical void. It is beginning a journey to a thriving civilization of microorganisms, waiting to clean up after us silently, efficiently, and endlessly. These unseen allies are the true, tireless guardians of our environment, a powerful testament to the fact that even the tiniest, most overlooked forms of life can make the biggest and most profound difference to our world. Every day, billions of liters of wastewater flow through treatment plants across the world. When most people think about this, they imagine waste something to get rid of. But in reality, wastewater is a resource waiting to be unlocked. Inside that murky mix lies energy, chemical, biological, and even thermal. And modern engineers have learned to harness it. The journey begins with sludge, the thick semi-solid material left behind after the main treatment processes. For decades, sludge was considered a nuisance, something to bury or burn. But today, it's the backbone of the circular economy. Why? Because sludge is rich in organic matter, and organic matter means potential energy. In the heart of advanced treatment plants, enormous sealed tanks called anaerobic digesters transform this sludge into biogas. These tanks operate without oxygen, creating the perfect environment for specialized microorganisms known as methanogens. These microbes consume the organic material and release methane, the main component of natural gas. Its nature, as way of recycling carbon, turning yesterday's waste into tomorrow's power. The biogas that bubbles up from these digesters isn't just vented into the air. It's captured, cleaned, and used. Some plants use it to generate electricity on-site, powering pumps, blowers, and lights. Others compress it into biomethane, injecting it into city gas networks or using it to fuel vehicles. In Denmark, for example, entire bus fleets run on biogas produced from wastewater treatment plants. What was once discarded has now become a source of renewable energy. But the innovation doesn't stop there. The leftover material from digestion, called biosolids, can be further processed and reused after careful stabilization and drying. These biosolids can serve as soil conditioners, improving farmland fertility and structure. Of course, this requires strict control to ensure safety, removing pathogens and heavy metals. But when done right, it closes the loop beautifully. Nutrients return to the soil, and water returns to nature. In cutting-edge systems, thermal hydrolysis is used before digestion. This process uses high-pressure steam to break down complex organic molecules, making digestion faster and gas yields higher. Imagine it as pre-cooking the sludge: more surface area, more energy, less time. London's Thames Water Beckton plant, for instance, generates enough renewable electricity to power over 60,000 homes. What's truly exciting is how digital monitoring now optimizes every part of this process. Sensors track methane concentration, temperature, and pressure, while AI systems predict the best operational parameters. We're re-entering an era where wastewater plants are no longer just environmental facilities. They are mini power plants, energy hubs that balance ecology and economy. So the next time you see a wastewater facility, don't think of it as a place that just treats waste. Think of it as a living organism that breathes energy, captures carbon, and gives back to the planet. In a world struggling with energy crises and climate change, these humble tanks may just hold part of the answer. Let us imagine a world where water never truly becomes waste, a world where every single drop that leaves our homes, our industries, or our farms can find a new purpose, a new life. This isn't a scene from a distant science fiction movie. It's happening right now, all around us. The concept is called water reuse or water reclamation, and it's completely revolutionizing the way we think about sustainability and our relationship with this precious resource. It's a paradigm shift, moving from a linear, throwaway culture to a circular, intelligent one. For generations, we saw water as something to be consumed and discarded, but now we're finally starting to understand its true cyclical nature. This is the story of how we are learning to close the loop. For centuries, our approach to water management has been incredibly linear. We take fresh water from rivers, lakes, or underground aquifers. We use it once for our daily needs. And then we discharge the used water back into the environment, often carrying with it the byproducts of our civilization. But the modern world is waking up to a stark reality. This one-way model is no longer sustainable. We are facing a perfect storm of challenges. Climate change is altering weather patterns, leading to more frequent and severe droughts. At the same time, global population growth and relentless urban expansion are putting extreme, unprecedented pressure on our finite freshwater sources. The numbers are sobering. By 2030, global demand for water is projected to exceed the available supply by a staggering 40%. This isn't a distant threat. It's a looming crisis. To survive, to thrive, we have no choice but to change our ways. We must close the loop. So, how do we transform what was once considered waste back into a valuable resource? The process is a marvel of modern engineering, and it begins right where conventional wastewater treatment ends. Once the wastewater has been thoroughly cleaned of solids, organic matter, and most common pathogens through primary and secondary treatment, a new, more advanced stage of purification takes over. This is where the magic truly happens. We employ a suite of sophisticated technologies like ultrafiltration, which uses membranes with microscopic pores to block out even the smallest suspended particles. Then comes reverse osmosis, a powerful process that forces water through an even finer membrane, removing dissolved salts, heavy metals, pharmaceuticals, and other microscopic contaminants. Finally, as a powerful safeguard, high-intensity ultraviolet disinfection zaps any remaining viruses or bacteria, rendering the water exceptionally pure. The result of this multi-barrier process isn't just clean water, it's water so pristine it often surpasses the quality of bottled drinking water. The applications for this reclaimed water are as diverse as the communities that produce it. In many agricultural regions, this highly treated water is a lifeline, used to irrigate crops and ensure food security, especially in arid climates. Industries use it for cooling systems, saving vast amounts of fresh water that would otherwise be drawn from rivers or lakes. It's also used to replenish our vital groundwater aquifers, a process known as managed aquifer recharge, where the purified water is allowed to percolate back into the earth, bolstering our natural underground reservoirs for future use. But some places are taking it a step further. They are purifying this water to such a high standard that it can be returned directly to the drinking water supplier process, known as direct potable reuse. Trailblazing projects. Like Singapore's renowned Uni Water program and the Orange County Water District in California, are pioneers in this field. They are successfully and safely turning wastewater into high-quality drinking water for millions of people, proving that this technology is not just feasible but essential for urban resilience. Of course, the technology is only half the battle. There's a significant psychological barrier to overcome what experts often refer to as the yuck factor. The idea of drinking water that was once in a sewer can be unsettling for many people, even if science proves it's perfectly safe. Overcoming this hesitation requires more than just engineering. It requires empathy, transparency, and education. Experience has shown that when the process is explained clearly and openly, public acceptance grows dramatically. Well-designed public education campaigns, guided tours of the advanced treatment facilities, and genuine community engagement have proven that understanding breeds trust. When people see the science for themselves and understand the rigorous safety checks involved, fear gives way to confidence. After all, nature itself has been the ultimate water recycler for billions of years. Every drop of water on Earth has been recycled countless times through the natural water cycle of evaporation, condensation, and precipitation. In a way, we are simply learning to replicate nature's genius. The environmental benefits of closing the loop are enormous, and for it. By reusing water, we drastically reduce the need to extract new fresh water from our already strained rivers, lakes, and aquifers. This helps protect and restore aquatic ecosystems, allowing them to flourish. It also prevents the discharge of treated effluent, which, even when clean, can alter the temperature and chemistry of natural water bodies. Perhaps most importantly, water reuse provides a steady, reliable, and drought-resistant source of supply. Cities that embrace reuse systems build incredible resilience. They are no longer solely dependent on unpredictable rainfall or distant water sources. They gain a measure of water independence that allows their communities and economies to thrive, even in times of extreme scarcity. It's a powerful shift from a position of vulnerability to one of security. This isn't just about saving water. It's about ensuring stability, security, and ultimately peace for future generations. And the story doesn't end here. Innovation continues to push the boundaries of what's possible. We are entering an era of smart water management. Artificial intelligence algorithms now monitor water quality in real time, 24/7, automatically adjusting filtration rates and chemical dosing with a level of precision that was previously unimaginable. This not only improves safety, but also optimizes energy and resource consumption. Smart grids are being developed to intelligently distribute reclaimed water to where it is needed most, from irrigating urban green roofs and parks to supplying high-tech vertical and hydroponic farms that grow food right in the heart of our cities. Looking ahead, the vision is even more decentralized. Imagine a future where every building, or even every home, could have its own miniature treatment plant, capturing and recycling grey water from sinks and showers on site. This would create a hyperlocal source of water for non-potable uses, like flushing toilets or watering gardens, further reducing the strain on our centralized systems. So, when we talk about closing the loop, we're really talking about something much deeper than just engineering. We're talking about closing the gap between human activity and natural cycles, between technological advancement and our fundamental responsibility as stewards of this planet. Water reuse is not just a technical achievement, it represents a profound cultural shift. It challenges us to rethink our definition of waste and to see value where we once saw none. It's a powerful reminder that sustainability isn't about sacrifice or going without. It's about intelligence, innovation, and working in harmony with the world around us. Because the cleanest, safest, and most sustainable drop of water might just be the one we've already used. The story of wastewater treatment began thousands of years ago with simple drains carved into stone. Today, it stands at the cutting edge of science, merging biology, chemistry, and artificial intelligence. The future of water is smart, tabulating, and sustainable. It starts with one of the most powerful innovations of our time, membrane bioreactors. For centuries, the process was straightforward. Separate the big stuff, let nature do the rest. But as our cities grew, so did the challenges. We needed something faster, smaller, and more powerful. We needed a revolution. That revolution is the membrane bioreactor, or MBR. Imagine combining the two most crucial steps of water treatment, biological breakdown and physical filtration, into one elegant, super-efficient system. In traditional plants, these are separate stages, but MBRs weave them together. Inside an MBR tank, a bustling ecosystem of helpful microorganisms breaks down organic matter, just like in a conventional system. But here's where the magic happens. Submerged directly in this mix are bundles of ultrafine membranes, with pores so tiny they're measured in nanometers, 1,000 times smaller than a human hair. These membranes act as microscopic gatekeepers. They allow pure water molecules to pass through under gentle suction, but physically block almost everything else: suspended solids, bacteria, and even viruses. The result is extraordinary. We get a compact, high-efficiency process that produces water so clean, it can often be reused directly for things like irrigation or industrial processes. It's like having a microscopic guardian for every single drop of water. This isn't just an upgrade, it's a paradigm shift. You might think this sounds like science fiction, a technology for a distant future. But MBRs are already here, quietly transforming cities across Japan, the United States, and Europe. Because they combine steps, these systems can occupy just a fraction of the space of old treatment plants. This is a game changer for densely populated urban areas where land is a precious commodity. Old, sprawling facilities can be replaced with compact, modern ones, freeing up land for parks, housing, or community spaces. And they're becoming smarter about energy. To early criticisms focused on the power needed to pump water through the membranes. But today's systems use advanced, energy-efficient aeration techniques that gently bubble air to both scour the membranes and provide oxygen for the microbes. They consume less power while delivering a far superior quality of water. It's the perfect harmony of biology and engineering, working in sync to achieve what was once thought impossible. But the next great leap forward isn't just about hardware, it's about intelligence. The real revolution is coming from artificial intelligence. Modern treatment plants are evolving from mechanical facilities into living, breathing digital ecosystems. Thousands of sensors are embedded throughout the system, tracking every conceivable variable in real time. The flow rate of incoming water, its temperature, dissolved oxygen levels, pH balance, and the concentration of nutrients like nitrogen and phosphorus. Each second, a torrent of data points more than any team of humans could ever hope to process, streamed into powerful machine learning algorithms. These algorithms don't just display data, they interpret it. They learn the plant's unique rhythm, predict changes, adjust processes on the fly, and optimize everything for maximum efficiency and safety. These AI-driven systems are not merely reactive, they are predictive. They learned. Over time, they recognize subtle seasonal patterns, like how rainfall affects water composition in the spring versus the fall. They anticipate sudden surges in demand, like after a major sporting event, and prepare the system in advance. They can even detect the signature of an industrial chemical spill upstream before it reaches a critical concentration, triggering alarms and preventative measures automatically. This predictive power extends to the machinery itself. Instead of replacing pumps or cleaning membranes on a fixed schedule, AI predicts exactly when maintenance is needed based on real performance data. This reduces downtime, cuts costs, and extends the life of expensive equipment. The plant becomes almost a live, self-regulating, cybernetic organism where steel, software, and biology coexist in perfect harmony. Now, let's zoom out. Imagine not just one smart plant, but entire cities connected through an intelligent water network. This is the vision of the Internet of Water. Smart pipes equipped with acoustic sensors could detect the faint hiss of a leak and pinpoint its location instantly, saving billions of gallons of lost water. Sensors buried in the ground could monitor groundwater recharge, ensuring we manage our aquifers sustainably. All this data would flow to cloud-based dashboards, accessible not just to engineers in a control room, but to citizens on their smartphones. In this vision, transparency builds trust. People can literally see where their water comes from, how it's being treated, and where it goes. This isn't just about efficiency, it's about reconnecting us to the most vital resource of our civilization and fostering a shared sense of responsibility. And the innovation goes even deeper, reaching into the very building blocks of matter. Researchers are exploring using microalgae to capture carbon dioxide produced during treatment and use it to grow biomass for biofuels, turning a waste product into a source of green energy. New nanomaterials promise the creation of ultra-selective membranes that can target and remove even the tiniest trace contaminants, like pharmaceuticals, that slip through conventional systems. And emerging technologies like blockchain may soon be used to create an unchangeable, transparent record of water quality data, guaranteeing accountability from the source all the way to your tap. So, As we look to the future, we realize that wastewater treatment is no longer just about cleaning water. It's about fundamentally redefining how our civilization operates. It's about creating circular economies where nothing is truly wasted. The fusion of biology and technology gives us a tangible hope for a world where every drop is valued, where innovation and nature finally flow together in harmony. The next chapter in our relationship with water isn't waiting to be written, it's already here. Thank you so much for joining us on this journey. If you found this fascinating, please consider liking this video and subscribing to our channel for more stories about the hidden science that shapes our world. We'll see you in the next one.